Hey everyone, and welcome to the 8th video on the D-block chemistry, and this will be the last video that makes up lecture 9. And in this lecture, I've said it's an introduction to crystal field theory, but really what it is, we'll have a summary of all the other things we've seen so far, sort of the advantages of using this Lewis acid, Lewis base model to show how complexes exist. So yeah, not so much a revision summary, but more like, why this model works and its advantages, but then also why it doesn't work and why we actually need a better theory to explain a lot of things we can't already. And then I'll give a very brief introduction into what crystal field theory is and how it works, but then all the actual real chemistry and calculations we'll go on to in lecture 10. So far we've looked at this Lewis acid and base model, and it has had its advantages. So it's been perfect for explaining the existence of coordination complexes, for example, and how the bonding works, why they essentially why they exist, like how a metal cation can have 6 waters around it, or 4 ammonias and 2 waters around it, and like this idea of the Lewis acid and the Lewis base works very well and is quite accurate. It also allows us to predict quite reasonably the shape of what some compounds will be from their coordination number. So if there's 3, we can imagine it's trigonal planar, and if there's 2, it's linear. 4 is where things start falling apart, really. And it does it the same way as VSEPR, as we said. So it wants to minimize repulsions, and this is again some fair science and some fair basing for the model. What is very good at, actually, I find, is the explanation of reactivity and stability through hard and soft classification. So what we went in the last video, the hard acids like to make complexes with the hard bases, and the soft acids like to make complexes with the soft bases. That is really the highlight, I think. You won't get that with crystal field theory. You get a lot of other advantages, but we can't explain the reactivity and stability without this hard and soft classification. And the other thing that's really nice is the description of the ionic and covalent nature of the bonding through this hard and soft classification. Again, we won't get that from crystal field theory either. So that's, yes, a good advantage of the Lewis acid and Lewis base model. It does, however, have a lot of disadvantages, otherwise we wouldn't be searching for a better model. So on the note of predicting the structures and the geometry, we were saying the Lewis acid base model does a reasonable job, but it doesn't do a perfect job, especially when it comes to a coordination number of 4, which is actually quite a common one, as we'll be seeing, is really pretty common. It doesn't explain the existence of square planar geometry, and it certainly doesn't explain the preference for some complexes wanting to make a square planar geometry rather than a tetrahedral. And that we can do with crystal field theory, and we will do in the next lecture. It also, some of the geometries change. So octahedral, as I said in the last video, is, or 2 videos ago, the most common geometry for the first row transition metals. But sometimes the octahedron can even be distorted. And this, again, can't be explained with the Lewis acid base model. We need to use crystal field theory. One of the other things it can't do is explain the colourful nature of complexes. So it's one of the biggest things about these inorganic complexes are their colours. So here I've got an example of an experiment, like a doodle of an experiment, that shows what changing the ligands can do. So if we start with chromium with 6 hydroxide anions around it, it's a nice sort of dark green, racing green, I guess. And then if you change these hydroxide ligands for water, and with some of these experiments, I don't know what it is for chromium, but some of the complexes, it really can be as simple as the complex will be in water. If you add ammonia, the ligands will change to, at least some of them, being ammonia. So these can be quite simple experiments. But if you change the hydroxide to water, you can see it already becomes like this dark mauve sort of purple colour. And then if the water gets exchanged to ammonia, then it becomes a really bright, not quite lilac, but purple colour. And this can't be explained by the Lewis acid or base model. Also, the magnetic properties of complexes. So we won't go into this in too much detail actually, but they do have paramagnetism, which we talked about a bit in the p-block elements. They exhibit that with unpaired electrons in some complexes, but not others, and we can't explain that. But what can help us explain all of these is considering the actual d orbitals their interaction with ligands and how the electrons then fill the orbitals, because that is essentially what dictates everything, how the electrons fill the orbitals and how they will then want to interact with other things. And that brings us to crystal field theory. So this is, instead of being a Lewis acid, Lewis base model, which is quite correct and works, but as I said has its limitations, this is more of an electrostatic model that describes the ligands as metals as point charges. So therefore that's why we lose out this whole thing about hard and soft acids and bases. We don't get any of the ionic covalent nature so easily described. What it does do is that the attraction between these charges is what holds the complex together, and then the repulsion between ligands and certain d orbitals splits the d orbitals. I've got a little diagram here that I'll explain in a lot more detail in the next lecture, but this is kind of the basis of crystal field theory. So we've got 5 degenerate d orbitals, as we've always seen. There are 5 d orbitals, but when ligands approach, they can split in various ways. This is an example for an octahedron, but it changes to have 2 high energy orbitals and 3 lower energy orbitals. And this is really key to everything from the shapes and especially the colour and magnetism derives from this. And this is also why I was putting so much emphasis on working out the electronic configuration from oxidation states, because once we know where the orbitals look at, what the orbitals look like even, we need to know the electronic configuration so we know where to put the electrons. And by looking at the energy of these, we can explain everything from why certain geometries are stabilized whereas others aren't, and through the transitions we can explain the origins of color. So this will all come in the next lecture, but it's just like a nice way to describe why what we've had so far works to an extent, but we need something new. Finally, there aren't so many questions in the back of the book for this section, so it's just questions 3 and 9 on page 1301. That are good for this lecture. Next lecture, it seems like there are a lot of questions, so it will all balance out.